بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف عبد الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. الآن مع الحلقة الثالثة من سلسلة الستاندر موديل، وحلقتي أنا رقم 31 رقم 32 التي تتحدث عن كتلة الفيرميون. في الحلقة السابقة عرفنا كيف يعطي الهيجز كتلته لل WZ وذلك عن طريق عن طريق نظريته، هو أن مثل المجال الكهربائي يتحول إلى مجال مغناطيسي، أو يضعف المجال الكهربائي ليزيد المجال المغناطيسي، بالرغم من أنه الطاقة الكلية ثابتة، لكن المجال الكهربائي يضعف ويزيد المجال المغناطيسي. هذا مثل الطاقة الكلية لجسم ساقط على سطح الأرض، نجد أن الطاقة الكلية ثابتة، ولكن طاقة الوضع تنقص، بينما تزيد طاقة الحركة كلما تتجه نحو مركز الأرض أو نحو سطح الأرض. وأيضا عرفنا بعض الخصائص الجميلة جدا التي فسرتها نظريتي، مثل لماذا لم تستطع هذا النموذج تتبع نمو وتطور الكتلة، لأنه بصراحة هو أهمل الجزء المتعلق بالمجال الكهربائي وتحول إلى المجال المغناطيسي فقط، وبالتالي حسب الكتلة من المجال المغناطيسي، مثلما نحن نحاول أن نحسب الكتلة من الطاقة الحركية. لكن إذا أخذنا في الاعتبار طاقة الوضع مع طاقة الحركة، يمكننا تتبع تطور الكتلة. طبعا هذا الكلام لا يظهر على سطح الأرض، لأن سطح الأرض جاذبيتها ضعيفة، لكن طاقة الحركة وطاقة الوضع تؤثران على الكتلة. الكتلة ليست ثابتة، تؤثران على الكتلة. في التفاعلات دون الذرية هذا الأمر واضح جدا، لأنه يتعلق بما يسمى بمعدلات تدفق الزمان والمكان، ومعدلات تدفق الزمان والمكان تختلف حسب طاقة التفاعل، وحسب نوع التفاعل، وحسب درجة تصادمات الجزيئات والمنطقة التي تصادم بها الجزيئات. لهذا نجد أن الكتلة يمكن تتبعها بهذه الآلية، لكن نجد أن النموذج المعياري أهمل خصائص المجال الكهربائي التي تعتمد على الاشتقاقات الزمنية، وأبقى الخصائص المغناطيسية التي تعتمد على الاشتقاقات المكانية. الآن هنا في كتلة الفيرميون، تعال نشوف ماذا سنستكشف. أيضا من الأشياء اللي استكشفناها أن الديريفيتيف كوفارينت ديريفيتيف ما زال متابعنا. هذا الكوفارينت ديريفيتيف الذي أوجدت له قاعدة خاصة، بحيث أنه الكوفارينت ديريفيتيف في الفضاء الكثيف أو المشتقة بالنسبة للأبعاد في الفضاء الكثيف يختلف تماما عن المشتقة أو الاشتقاقات في الفضاء الخفيف الذي فضاءنا نحن. فالفضاء الكثيف الاشتقاقات تختلف تماما عن الاشتقاقات في الفضاء العادي، وحسب الجيج انفاريانس يجب أن تنتقل هذه الاشتقاقات. جيج انفاريانس جيج لا يتغير تحت هذه الاشتقاقات. ما دام فرضنا هذا الفرض، فهذا أنه عند الاشتقاقات في ذلك الفضاء بالنسبة لفضاءنا نحن يساوي ذلك الفضاء اللي هو دي كابيتال ميو. هذا الاشتقاق بالنسبة لفضاءنا نحن يساوي الاشتقاق في فضاءنا نحن زائد كمية. هذه الكمية التي تعبر عن الجيج انفاريانت. الحمد لله شكر الله. هذه الكمية التي تعبر عن الجيج انفاريانس يجب أن تحمل في داخلها كسر معين في السيمتري، وهذا الكسر هو عبارة عن الانتقال من المجال الكهربائي المعتمد على الزمن والمسافة طبعا إلى المجال المغناطيسي الذي يعتمد على المسافة كليا. بالتالي المجال الكهربائي لديه اشتقاقات زمنية، المجال المغناطيسي لديه اشتقاقات مكانية فقط. هذا الفرق بين المجال الكهربائي والمجال المغناطيسي بحيث يطابق أو يتناسب مع الفرق بين الاشتقاقات الزمانية والاشتقاقات المكانية تظهر في المعادلة التي تكون بعد الدي ميو الصغيرة مباشرة. يعني كابيتال دي ميو يساوي سمول دي ميو زائد هذا الحد. هذا الحد هو ما نعول عليه في أنه نستكشف أشياء خافية عن النموذج المعياري وظهرت في نظرية علي يوسف. هذا الحد ما زال متابعنا من المحاضرة الأولى، ما زال متابعنا. تابعنا في التفاعلات بين الجيج وبين الفيرميون، تابعنا في تفاعلات الهيجز مع الجيج. الآن في كتلة الفيرميون تعال نشوف اللي هو أعتقد أنه بين الجيج والفيرميون حيث يعطى الكتلة للفيرميون. تعال نشوف هل يتابعنا أم لا. طيب فلنبدأ بسم الله.
Okay, then I would say let us begin and continue with our electroweak theory lecture. The last time we already began to discuss spontaneous symmetry breaking in the standard model and how the masses are generated of the various particles. And we already looked at the masses of the vector bosons, the W and the Z boson. And the next topic is the generation of fermion masses, namely the masses of quarks and leptons. And remember that we currently only look at one generation of fermions, so one generation of leptons. And therefore, let us immediately begin by plugging in the expression in unitary gauge that we have obtained the last time. Unitary gauge means that we gauge away the unphysical components of the Higgs doublet, and what remains is only the physical Higgs field, which is real, and the vacuum expectation value, which is also real, in the lower component of the Higgs field. Maybe just to remember, the unitary gauge version of the Higgs doublet is this one. So the upper component is 0, the lower component is real, and is written as a constant V plus a Higgs field H, which depends on X, normalized by square root of 2. So if we plug this unitary gauge into the Yukawa Lagrangian, then we obtain the mass terms of the quarks and leptons. So let us write it down, Yukawa in unitary gauge becomes, so the first Yukawa term is the one for the leptons, YE, Yukawa coupling for the leptons, YE times the left, let me do it for one term explicitly, L bar phi ER plus the Hermitian conjugate, okay, plus all the additional terms. And what happens if you plug in now the unitary gauge for the Higgs doublet? Only the lower component of phi is non-zero, the upper component vanishes. Therefore, in the multiplication with L bar is also a doublet. In the upper component it contains the neutrino, in the lower component it contains the left-handed electron. So the neutrino drops out, it's multiplied with 0, and the left-handed electron is multiplied with exactly this combination. Therefore we obtain YE times V plus H divided by square root of 2 times the left-handed electron bar times the right-handed electron. And as you know, this expression here times a constant is a mass term for an electron. And here we also see that it is not only multiplied by a constant but also by the Higgs field, which means that we have an interaction between the Higgs field and the electron. But let us go on for the other two terms. There is also the down quark term, which has exactly the same structure. With exactly this combination, therefore we obtain.
طبعا إذا الماس تيرم بالنسبة للفيرميون عن طريق اليوكاوا انتراكشن. يعني اليوكاوا انتراكشن هو الذي يعطينا الماس تيرم بالنسبة للفيرميون. رأينا في الفيديو السابق أن الماس تيرم أو الماس الذي نأخذه من الهيجز إلى الجيج لا يتعلق باليوكاوا، شيء غريب جدا، وإنما يتعلق بالكاينتيك انرجي بالنسبة للجيج، بالإضافة إلى البوتنشال بالنسبة للهيجز. هنا طبعا احتملنا أيضا البوتنشال بالنسبة للهيجز، لكن اعتمدناه مع اليوكاوا تيرم. يعني الماس الذي يعني الكتلة الفيرميون، فنجمع بين الاثنين، الجهد ليوكاوا، الجهد لهيجز، بالإضافة إلى اللاجرانج الخاص بيوكاوا. هذا ما يختص الفيرميون. وما يختص الجيج الطاقة الحركية أو اللاجرانج الحركي اللي هو كاينتيك لاجرانج بالنسبة للجيج مع الهيجز تيرم. إذا الهيجز تيرم هو ثابت. هناك أيضا بالمناسبة هناك أيضا التفاعل مع الجيج مع الفيرميون. بالمناسبة هذا نسيناه. الجيج مع الفيرميون يعطينا عن طريق الجيج مع الفيرميون. كان في أول محاضرة ولا ثاني محاضرة عن طريق معادلة اللاجرانج الخاص لا هذا لا يعتبر ماس تيرم. هذا ليس للماس، هو للانتراكشن فقط، اللي هو الطاقة الحركية للجيج مع الطاقة الحركية على ما أعتقد للفيرميون. وهذا للانتراكشن فقط، لكن ليس للماس تيرم. الماس تيرم هو ليوكاوا حيث فيه الرايت والليفت. الرايت والليفت الفرق بينهما هو الذي يعطينا الماس، وهذا واضح أن الرايت يعتمد على الاشتقاقات الزمنية والليفت يعتمد على الاشتقاقات المكانية بالنسبة للفيرميون. وفي الجيج رأينا الكاينتيك انرجي للجيج الذي أيضا تعتمد على فاي بار، أو تعتمد على دي ميو تربيع، دي ميو فاي تربيع، دي ميو فاي كل تربيع مع اليوكاوا مع الهيجز تيرم الذي هو عبارة عن بوتنشال هيجز. أعطانا الكتلة للجيج اللي هو الدبليو والزي. هنا يوكاوا مع الهيجز تيرم مرة أخرى.
YE times V plus H divided by square root of 2 times the left-handed electron bar times the right-handed electron. And as you know, this expression here times a constant is a mass term for an electron. And here we also see that it is not only multiplied by a constant but also by the Higgs field, which means that we have an interaction between the Higgs field and the electron. But let us go on for the other two terms. There is also the down quark term, which has exactly the same structure. YD for down quarks times V plus H divided by square root of 2 times down quark left times down quark right. And then there is finally the up quark term, YU times V plus H divided by square root of 2. And there we have this multiplication with the epsilon tensor. The epsilon tensor is such that the upper component of the up quark doublet is multiplied with the lower component of phi, and therefore we now get up quark left times up quark right times V plus H. And then we get for all of this also the Hermitian conjugate part. And so then we can define masses. MF for all the fermions is defined as the corresponding Yukawa coupling YF times V divided by square root of 2. And then the Yukawa Lagrangian simply becomes L Yukawa is equal to the sum over all the types of fermions, namely F equal electron down quark and up quark, and each time we have mf times f bar f times, we can write this as times 1 plus Higgs field divided by V. So here we assume that the Yukawa couplings are real. See section 2. In section 2, where we discuss 3 generations, we will discuss in more details why we can assume that the Yukawa couplings are real and what are further connections to this, but here we simply assume it. And then the mass terms are of course also real, and in the sum of the term plus its complex conjugated, the coupling prefactor stays what it is, and we just get this plus its Hermitian conjugate, which in the end gives just a full left plus right-handed f bar f. Yes. As you see, there are exactly 3 Yukawa couplings. In principle, they could be complex. And there are 3 types of fermions, namely lepton, down quark, and up quark, and therefore there are as many Yukawa couplings as fermions. So the answer is yes. And that will maybe change in 3 generations, because then the Yukawas will become matrices. Like the WEF, be careful. We will discuss more about the role of the WEF and versus input parameters in the exercise sheet. But the WEF is of course an output, not an input. At least the natural way to look at it is that the WEF is an output. The input would be the Higgs potential. Its minimum is a function of the Higgs potential parameters. And so the WEF would be an output. But of course you can invert this relationship. But here there are as many Yukawa couplings as there are masses, and therefore you can regard the Yukawa couplings as input and the masses as output, or you can invert the relationship and regard the masses as input and the Yukawas as output. But here there is nothing particularly deep about this, and this relationship will be much more complicated in the case of 3 generations. Okay, so we have obtained the Yukawa Lagrangian, and we see that there is a minus also. It generates mass terms for the fermions, quarks and leptons, but not for the neutrino. And along with the mass, there is always an interaction of this form, h divided by v with the same prefactor.
طبعا ما عدا النيوترينو، هذا يعني أن النيوترينو لديه خصائص كهربائية، لأنه ذكر ما عدا النيوترينو، وبالتالي الانتقال من الخصائص الكهربائية إلى الخصائص المغناطيسية ينقص هذا الأمر، بالرغم من أنني ليس مقتنعا تماما بما أقوله. لهذا يعني تعالوا لا نسبق الأحداث، لكن أنا نقلت هذا بناء على الفوتون وما اشتغلناه في الجيج اللي هو الجيج ماس، عندما أعطى الهيجز طاقته أو كتلته للجيج، استثنينا الفوتون بحذفنا للخواص الكهربائية أو اعتماد المجال الكهربائي على الاشتقاقات الزمنية. تعالوا نشوف هل يحصل هذا الأمر هنا في النيوترينو أم لا.
So let me summarize then. In total, what do we have in the full standard model after electroweak symmetry breaking, including this discussion, but also the discussion from last week? We have now the following particle content. We have a massless spin 1 vector boson, which is the photon. We have massive spin 1 vector bosons W plus minus and the Z boson with masses MW and MZ. We have massive Higgs boson, the Higgs with spin 0 of course, and we have massive fermions, up quark, down quark and electron, and we have a massless neutrino which exists only in the left hand of pole. This is the particle content after spontaneous symmetry breaking, and there are unphysical degrees of freedom, namely the would-be Goldstone bosons, which we have gauged away by using unitary gauge, and the unphysical degrees of freedom of the vector bosons. And in all cases, by going through the derivations once again from last week we skipped that detail, but it's obvious that the same happens as with the fermions, namely each time the mass terms are accompanied by such a factor 1 plus h divided by v, because initially the only thing that appears in the Lagrangian is such a combination. That means wherever you have a term with a vacuum expectation value, the term actually contains v plus h, or in other words, v times 1 plus h over v. Therefore, all the mass terms are accompanied by that factor. And so let me just write it down. So schematically, we have the mass term for the W plus minus times mw square, which would be accompanied by 1 plus h over v square. Similarly, the mass term for the Z boson mz square times mz square times 1 plus h over v. And also for the fermions, we have a fermion mass term which is linear squared times 1 plus h over v. So in all terms, the masses are accompanied by interactions with the Higgs bosons. Such that the interaction of the Higgs with anything is always proportional to the mass. So, okay, let me just write it here as in the case of the fermions, that this interaction is proportional to mf over v, and similarly for the vector boson. So in all cases you get the relation that the interaction strength by which the Higgs field interacts with other fields for which it generates the mass, the interaction is proportional to the respective mass. This is of course a prediction of the Higgs mechanism of the standard model, and that is being tested experimentally. So,
طبعا هيجز يمثل الخصائص الكهربائية، اعتماد على الخصائص الكهربائية، هذا ما يمثله هيجز. وفي نظرية تقول الانتقال في هذا السيمتري المكسور في بخارج الكتلة داخل الكتلة، الانتقال إلى من الخصائص الكهربائية المجارية، مجال الكهربائي، إلى الخصائص المغناطيسية، المجال المغناطيسي، يعطي الكتل. لا يعطي الكتل. أقول أن تتناثر مع الكتل. هذا هو الفرق، فرق كبير جدا. تتناثر مع الكتل لأنه هي أصلا انتقال من خارج الكتل إلى داخل الكتل، أو من فضاء غير كثيف إلى فضاء كثيف، كثيف لدرجة يعني كثيف كبير، درجة بعيدة جدا. هذا الكثافة هو يشابه تماما الانتقال من خارج الكتلة إلى داخل الكتلة، وبالتالي أصلا الكتلة موجودة، أو الفضاء أو الطاقة أصلا موجودة. هذه الطاقة في هذا التناظر المكسور يعطي الكتل، ممكن نقول ذلك يعطي الكتل. لكن المهم هناك تناسب بين الانتقال من المجال الكهربائي، الخصائص الكهربائية، للخصائص المغناطيسية. هذا الانتقال يشبه تماما الانتقال من خارج الكتلة إلى داخل الكتلة، وبذلك العلماء شعروا أو فسروا هذا الانتقال إلى أن الهيجز أعطى الكتلة. هو لم يعطي الكتلة، هو طبعا الخصائص الكهربائية تمحى وتقمع وتبقى الخصائص المغناطيسية كما ذكرنا مثل طاقة الوضع وطاقة الحركة. نجد أن زيادة طاقة الحركة طاقة الوضع تضعف وطاقة الحركة تزيد. هذا ما يحدث، لكن هذا كله في ظل التناظر المكسور، في ظل التناظر المكسور. وكأنما هذا الكسر لديه خاصية عجيبة. تعالوا نشوف هذه الخاصية. خاصية الكسر من هذه المعادلة تخبرنا الانتقال من الحد الأول اللي هو النص مضروبة في 1 زائد اللوغاريتم الطبيعي لسي أس 6 16 جي تربيع ام تربيع إلى الحد الثاني اللي هو 2 جي ام على سي تربيع ار. هذا الانتقال دونما يغير النسبة العامة الدي ار على سي دي تي. كأنما هذا يعني أنك تنتقل، كأنك انتقلت من الموجب إلى السالب. هذا الحد هو موجب والحد الذي أمامه إشارة سالب يعتبر سالب، وهذا الحد يعني متناظران بحيث أنه نقص هذا الحد يزيد هذا ذاك الحد وهكذا. فإذا انتقلت من الحد الأمام إلى الحد الخلف، طبعا هذا الانتقال يجب أن يكون ذو رقم متساوي. الأرقام يجب أن تكون متساوية. يعني مثلا الحد الذي أمام هو عبارة عن 10، تنتقل الحد الذي الخلف هو مفترض يكون 10، وهذا مستحيل. لماذا مستحيل؟ لأن الكتلة هنا تعمل عكس هناك. الكتلة هنا تنقص هذا الحد، والكتلة هناك تعمل زيادة هذا الحد. وهذا يشبه تماما بالانتقال بين طاقة الحركة لطاقة الوضع. تنقص طاقة الوضع وتزيد طاقة الحركة. الكتلة تتصرف مثل هذا، أيضا الطاقة تتصرف من هذا. والحد الثاني هو معادلة شوارشيرد المعروفة 2 جي ام على سي تربيع ار. هذه معادلة شوارشيرد المعروفة التي تخبرنا أنه إذا سيطر هذا الحد هذا يعني أننا داخل أفق الحدث للثقب الأسود. والحد الذي على الأمام الحد الذي بإشارة موجب اللي هو من النص انت يعني كل هذا الحد أو من إشارة سالبة للأمام، هذا الحد يعتبر خارج الثقب الأسود. ونحن نعلم أن داخل الثقب الأسود الفضاء ثنائي الأبعاد يفعل آليات للدفاع النفسي. يعني الطاقة إذا وصلت إلى هذه المرحلة الفضاء ثنائي الأبعاد يدافع عن نفسه. هناك شيء أريد أن أضيفه. إذن الانتقال من هذا إلى ذلك يجب أن يترافق تغير في الكتلة M. لهذا نجد أن العكس صحيح، أن التغير في الكتلة M تصاحب هذا الانتقال، والعكس هو صحيح، التغير في الكتلة M تؤدي إلى هذا الانتقال. يمكن اعتبار الحد الأول هو خواص الكهربائية التي تعتمد على الزمن، خواص المجال الكهربائي التي تعتمد على الزمن، والحد الثاني هو خواص المجال المغناطيسي الذي يعتمد على المكان فقط، والمجال الكهربائي يعتمد على الزمن. وبالتالي نجد أن الانتقال من الخواص الكهربائية إلى الخواص المغناطيسية تتحكم فيه الكتلة. وكأنما أعطينا الكتلة المجالات الأخرى، كأنما هيجز أعطى الكتلة للمجالات الأخرى، لكن هو أصلا الانتقال عبارة عن فيس ترانسيشن، وهذا الانتقال تتحكم فيه الكتلة.
So, then we have discussed the structure of spontaneous symmetry breaking in the electroweak standard model at 3 level for 1 generation. We have derived all the physical consequences of it, namely the masses of all particles. And just remember that for each of those fields and particles, the direct mass term would violate gauge invariance, but via the connection to the Higgs interactions, we get gauge invariant combinations of mass and interaction terms, and in particular, we generate all the masses of spin 1 and spin 1/2 particles. And the mass of the Higgs itself comes from the Higgs potential, and we have implicitly also calculated it. But now, having said all that, let us generalize this discussion and look not only at the standard model, but at the more general structure of spontaneous symmetry breaking in gauge theories. That more general understanding will also allow us to obtain a more convenient form of the standard model quantization compared to unitary gauge, namely the so-called RxI gauges, which are the gauges which are used in practical calculations. But I do not want to go directly to RxI gauges in the standard model, but I want to take a step back and do the general calculation first, because we do not only want to discuss RxI gauges, but also a few physical consequences which are better visible in the general setup. So let us discuss this. General mass generation and RxI gauges. So this chapter is a mix between interesting physics information and technicalities on gauge fixing. Let us start with something physical, namely generic spin 1 masses. So let us go away from the standard model and look at the generic gauge theory. A generic gauge theory will be now a gauge theory with a simple gauge group, so there is only one gauge coupling and one set of vector fields, and we will just define it by specifying the covariant derivative. Capital D mu is normal D mu plus I times G times TA times VA mu. So that means that we have one gauge coupling G, one set of generators TA. We do not specify what they are, but they will satisfy some Lie algebra relations. And we have one set of vector fields VA mu. And it doesn't matter what gauge group there is and how many gauge bosons there are. It is just some number. Okay. Then in this generic gauge theory we have some scalars. And in analogy to the standard model, let me assume these are complex scalar fields. Capital Phi with some index I, and again we do not specify what is the nature of that index. It is just some set of fields, and we write it as small phi I plus Vi. And so here again, the Vi should be the vacuum expectation value at tree level. And this should be small fluctuations around the vacuum. So in other words, in the vacuum, small phi I is 0. So small phi I parameterizes fluctuations around the vacuum, similar to the Higgs field here. And we do not put 1 over square root of 2, because in the generic case we do not know what is the correct normalization factor. Therefore we just put no normalization factor at all. And now we can look at gauge transformations. Gauge transformations of the scalars in general would be delta gauge, an infinitesimal gauge transformation with some parameter A. So you can, for any generator, you can do an infinitesimal gauge transformation of the scalars, phi I. And that would always be minus I times the generic gauge coupling times the generic generator TA times the Higgs field phi, and then the index structure. If you want the transformation of the component I, then you have here TA ij times the component phi j. Of course, using the covariant derivative, the kinetic term will be automatically gauge invariant under this gauge transformation, and we require the full the Lagrangian of that theory to be invariant under these gauge transformations. Now, the first consequence that we can derive, which is interesting, is what is the behavior of the vacuum under gauge transformations. Because the behavior of the vacuum signals whether we have spontaneous symmetry breaking or not. Spontaneous symmetry breaking means that the vacuum is not invariant under gauge transformations, and therefore we look at gauge transformations of the vacuum. So what is that? We take delta A, a gauge transformation of phi I, but go into the vacuum, and then what does it mean? It means that on the right hand side we plug in for the field the vacuum expectation value, and then we obtain minus I times G times TA Ij Vj. And this quantity is relevant because it signals whether we have spontaneous symmetry breaking or not. So up to the factor minus I, which is a normalization convention, let us give it a name. Let us call it small d. That will be like an order parameter. What is the index structure of d? D has one index A, and it has one index I. So that corresponds to how the vacuum behaves under a gauge transformation in the gauge direction A. And the vacuum consists of many Higgs field components, therefore this behavior must have this index I corresponding to the scalar multiplets of the theory. And what does it mean? You should view this as so for each A, this is a vector in the space of Higgs fields. And how many vectors are there? There are so many vectors as there are gauge fields in the theory. So for every gauge field or for every generator, you have a vector which tells you how the vacuum transforms under this particular gauge transformation. So vectors in field space for every A. And these dAs, they are like order parameters for spontaneous symmetry breaking. If they are all zero, then the vacuum is invariant under any gauge transformation, and if some of them are non-zero, then we have spontaneous symmetry breaking. Therefore, those are essential quantities which tell us about the symmetry breaking structure. Okay, so let's summarize this. We have this order parameter dAi, which are defined as G times TA Ij Vj, and we have spontaneous symmetry breaking if the dAi are non-zero. So you can view it as many different vectors, or you can view it as a matrix with two indices, namely A and I. These two indices live in different spaces, so it's a non-diagonal matrix. And the question is, how many symmetries are actually spontaneously broken? In the sense, there are many generators. All the generators generate independent gauge transformations. In the standard model, for example, there are 4 generators for SU3 and U1. And how many linearly independent breakings are there in the standard model? Out of the 4 generators, 3 are broken, 1 is unbroken. What does it mean in terms of this order parameter? Now the number of linearly independent spontaneously broken generators is the number of how many linearly independent linear combinations can you form out of these vectors dA. And it must be real linear combinations, because you are only allowed to do real linear combinations of gauge bosons and generators. So that the number of linearly independent DAs is simply the rank of this matrix. That is simply the rank of this matrix. And that can then be defined as the number of broken generators. Where there is just one small subtlety. You have to regard complex numbers as 2 by 2 matrices. Since we are talking about real linear combinations, therefore a complex number is like a 2-dimensional matrix, has rank 2. Okay, so for example, for the electroweak standard model, you would have here 4 Ds, namely the 3 TAs applied onto the vacuum and the hypercharge applied onto the vacuum. So these are 4 complex 2-dimensional vectors. So in terms of real numbers, these are 4 4-dimensional real vectors, and 2 out of the 4 are linearly dependent, and therefore the overall number of independent ones is 3. So this is how you see, in general, what is the symmetry structure of your vacuum, and the small dA is introduced as an important building block in the study of spontaneous symmetry breaking. Now, having said that, we can look at the mass generation in the generic case, and the mass comes from the interaction of the gauge bosons with the scalar fields, and that comes from the covariant derivative. So let us first evaluate the covariant derivative. Let's do it in the vacuum, because that generates the masses by coupling the gauge bosons to the vacuum. Okay, so in the vacuum, the ordinary derivative doesn't matter, and we get just plus I times G times the generators TA times the vector fields VA mu applied onto the vacuum, and the index structure, let's say if we put here the component I, then we have here Tij times Vj. And so what you see is that in the vacuum, the covariant derivative reduces exactly to that order parameter, namely we have here I times this PAI times VA mu. So that shows you that what remains is in the vacuum either 0 or vector boson times that order parameter dA. Therefore, if we go to the Lagrangian contains the covariant derivative of all the scalar fields squared. And in the vacuum, we now get from this term the square of the above. The I drops out, and then we simply have VA mu times DAI times another VB mu times dBi complex conjugated, and we sum over the I corresponding to the square here of each component I. So and that can be written in a more symmetric form by writing 1/2 times VA mu dB mu times the symmetric combination DAI dBi star plus the same thing with A and B exchanged, and we can define that as a mass matrix acting on the vector bosons. So we have derived here the structure of mass terms. We get a mass matrix M square AB with indices AB in the space of vector boson fields VA, VB, and the mass matrix square comes from the products of these order parameters. So let's write it in a nice way. So we obtain m square AB is equal to dAI dBi star plus the same thing with A and B exchanged. And here it is again nice to go back to the definition of the dAs and plug it in, because that is also illuminating. So if you plug in the definition, then we get the following. We get on the far left, we get V dagger, or Vi complex conjugated, or let's say, let's in general put Vi dagger. Then on the far right, we have Vj, and in between we have gauge coupling G times generator TA times gauge coupling G times generator TB plus the same thing with A and B exchange. So the mass matrix comes from products of two generators times two gauge couplings multiplied to the left and right with V dagger and V. So of course you know that the vector boson masses are proportional to the gauge coupling and proportional to the vacuum expectation value, but here you now see in full generality for any gauge theory how the mass matrix looks like. It is always this same structure. And you could go back and compare the electroweak standard model with that structure, and you see it is exactly the same. So what is now interesting, and let me squeeze that in here. This is a mass matrix. And what is interesting is the rank of the mass matrix, because the rank is the number of independent non-zero eigenvalues, and that corresponds to the number of massive gauge bosons. The non-zero eigenvalues correspond to the physical gauge boson masses, so the rank means how many gauge bosons will be massive. So the rank of this matrix is interesting, but what do we know about the rank? M is here a product of the matrix D times itself basically, and D is a matrix with a certain rank. So in general, the rank of the product of two matrices, if the rank of both is equal, will be again the same. If there are no artificial or completely accidental cancellations, the rank of this will be the same as the rank of D. But it cannot, for sure, cannot be bigger, it can at most be smaller. But the rank is equal or smaller to the rank of D. And so let me just squeeze that in here. Let us assume that there are no artificial accidental cancellations, and then the rank of M square AB is the same as the rank of D, which is the number of broken generators. And then for each spontaneously broken generator of the symmetry, we get one massive gauge boson. So you see all this that you already know here in completely general terms emerging. And that is the physical information that I wanted to tell you. Now let us do something a little bit more technical, which is however important in order to be able to calculate with the standard model. Namely, let us look at unphysical degrees of freedom, the so-called would-be Goldstone bosons. And that is easiest also here in the generic case. So, in the literature, if you are very explicit, these objects are called would-be Goldstone bosons because they are unphysical, therefore they can be gauged away and they do not appear as actually observable particles. But they appear in the same way as the ordinary Goldstone bosons in the case of a spontaneously broken symmetry. And they become unphysical because we do not only have a spontaneously broken symmetry, but on top of it we have gauge invariance and gauge redundancy, where we can gauge away certain degrees of freedom, and these are in this case the Goldstone bosons. I will often simply say Goldstone bosons and do not always spell out would-be, because it's just too time consuming. Okay, so let me define immediately
إذا هنا رأينا هذا الجيج فيكتور دي هذا الجيج فيكتور دي اي ورأينا الماستر كيف تعطى. هذه الماستر هي متناسبة مع هذه الماتريكس التي عبارة عن مضروبة جي فيكتور الدي فيكتور التي تعتبر جيج جولدستون بوزون. وطبعا جولدستون بوزون هي الاشتقاقات للمجال الكهربائي أو الاشتقاق للمجال الكهربائي المعتمد على الزمن. يعطي الكتلة في نظريتي هذا الانتقال من المجال الكهربائي المعتمد على الزمن إلى المجال المغناطيسي المعتمد على المسافة. هذه هو في نظريتي هكذا. طيب تعالوا نكمل.
Okay, so let me define immediately the generic would-be Goldstone boson in a way which is not directly the same as the Goldstone bosons we have defined in the standard model, but more generic. GA is defined as 2 times the real part of phi dagger I times d a I. Okay, so this is a definition where again this order parameter appears times the scalar fields of the theory, and here only the fluctuation part of the scalar fields appear, and this projects out some components out of all the scalar fields. And which components are projected out? These are exactly those would-be Goldstone bosons. The expression here is dimensionful, so the DAs, they are dimensionful objects because they contain the vacuum expectation value. So in order to obtain the Goldstone bosons we typically use in the standard model, one would apply some normalization factors which divide by the vacuum expectation value and so on to make the fields dimension 1 instead of dimension 2. But here on the generic level we do not do that because we don't know what is the correct or most appropriate normalization factor. Therefore we simply use this definition. What is an infinitesimal gauge transformation? Of these so defined would-be Goldstone fields. Let's do delta gauge with the index B onto GA. So now we have 2 indices. I define, okay, maybe let me add this point. I define for every generator a Goldstone field, but there are only a certain number of linearly independent DAs. Therefore, out of this construction, not all of the GAs are independent. Therefore, there is a certain number of linearly independent Goldstone fields, namely the same number as broken generators. And nevertheless, to make the notation uniform, I define the Goldstone fields for any A, and we should simply remember that we must not treat all of them as independent fields, but we only use the notation for convenience. Okay, but anyway, we can for each of them define a gauge transformation with gauge group index B, because we know what is the gauge transformation of this. It is written here. So now we use the Deckard version of it, and then we plug it in, and we obtain 2 times real part of then here minus G times phi I dagger times TB times I times DA I. So here with the full index structure. All right. And here we have now the full capital phi, including the vacuum expectation value. And if we plug in here the vacuum expectation value, then what we observe is that we get here another d. We get once again this order parameter d here on the left, d times another d, here d with index b, here d with index a. Therefore, what we get is exactly the mass matrix. So we get something proportional to the mass matrix m square ab times a constant plus terms linear in the small phi fields. So the interesting thing is that the Goldstone bosons transform into a term which is field independent, a constant, plus field dependent terms. So we have assumed that we are in the vacuum and we are looking at small fluctuations around the vacuum. Therefore, terms involving V are much bigger than terms which are linear in a field, because the field is a small fluctuation. Therefore, if you have here a gauge transformation of a very small fluctuating field, and one term in the gauge transformation is simply a constant proportional to V square, the other term is much smaller, then it tells you that by using that constant you can gauge away the original Goldstone fields. Even with an infinitesimal gauge transformation, you can arrange it such that after the gauge transformation, this Goldstone field becomes zero. So in other words, you could solve the equation. So put the set equal to, let's say, minus the original Goldstone field. And because that matrix has the same rank as the broken generators, and here there are also as many independent Goldstone fields as there are broken generators, so this is an equation that has a solution. So by solving the equation you can gauge away all Goldstone fields. All GA can be gauge transformed to zero. And this is the so-called unitary gauge. So this small exercise proves that the unitary gauge is always possible. Unitary gauge in which all these would-be Goldstone bosons are zero, and that also tells us that these would-be Goldstone fields are unphysical fields. However, we now want to look at general gauges where we do not gauge them away, but we keep them in the theory, and then our next few tasks have to do with how do these Goldstone fields appear in the Lagrangian and what one can we do with interpreting the corresponding terms. Yes. Yes, okay. So that is a detail which I didn't write down, and maybe we don't have to write it down. The small phi are now treated as the dynamical fields of our theory. Therefore, only they have a gauge transformation. So we would say that gauge transformation of the full phi is the same as the gauge transformation of the little phi, because obviously the gauge transformation of these numbers doesn't exist. So if you have a gauge transformation of that, the small phi inherits the same gauge transformation, whereas the V there is no gauge transformation of V defined. That explains it. Okay, so this establishes the structure of Goldstone bosons, and the fact that they can be gauged away implies that they are unphysical. But now let's keep them in the theory and look at the Lagrangian in the general case where the Goldstone bosons appear. So then we have this Lagrangian which contains the kinetic term of all the scalar fields phi I, from which we obtain the masses. And we have already seen what the mass term is, namely it contains this nice mass square matrix M square AB. But there we have neglected all the other terms which do not have that form. What happens if we fully expand this expression? If we fully expand that expression, we obtain the following. We obtain on the one hand the ordinary derivative, small d mu, of capital phi I. Then there are mixed terms between the ordinary derivative and the gauge boson interaction terms of that. And the mixed terms have exactly the form that we obtain derivative of these Goldstone boson fields times the vector boson fields. But if you expand it back, then you see that this means the derivative of phi Dagger, ordinary derivative of phi Dagger, times I times G times the gauge bosons times the generator. So it's exactly the mixed term coming from expanding the covariant derivative, just written by using the definition above. And then the last term is the one for the mass matrix, which we have already obtained, 1/2 m squared AB times dA VB. Plus higher order terms. So these are only the bilinear terms, bilinear in the fields, and the interaction terms, which are trilinear in the fields, and quartic, they are neglected. But this is the part of the Lagrangian which would correspond to the free field. And so here, then there are the nice mass terms, which are what we think would give rise to the masses of the gauge bosons. Here there are kinetic terms for all the fields, but here there are mixed terms, bilinear mixed terms between scalar fields and vector fields. And those mixed terms are, first of all, difficult to interpret, and even if we can interpret them, they are a drawback, and they make calculations more cumbersome and complicated, and therefore we should discuss those mixed terms in a more dedicated way. Let me clean the blackboard for a moment. So this is the final result of that subsection. We have discussed generic spin 1 masses. We have obtained a mass squared matrix. But if we incorporate the Goldstone bosons and do not choose unitary gauge, then there are mixed terms which would make it difficult to interpret what the mass term actually means. So in order to cope with that situation, we discuss another kind of gauge fixing, namely the so-called RXI gauges. And again, we do it first in the generic case, generic RXI gauges. So in QED, we often do the following. We must also use a gauge fixing in QED. There is something similar to unitary gauge in QED where we directly gauge away on physical fields, but very often we want a Lorentz covariant gauge fixing that looks like this. L fix is equal to -1/2 psi times d mu a mu square. This breaks gauge invariance in QED but is Lorentz invariant, and then we quantize QED in this way. Okay, let us now say maybe we can use the same gauge fixing also in our case here if we have spontaneous symmetry breaking. And actually that is possible. We can use the same gauge fixing here. But if we do that, then in our Lagrangian those mixed terms remain, and they remain a drawback in actual calculations and also in interpreting the physical degrees of freedom in our theory. Therefore, people have thought about how to obtain maybe an improved gauge fixing which is adapted to the case of spontaneous symmetry breaking. And that improved gauge fixing should on the one hand be kind of similar to the one in QED, where d mu, a mu or something like that appears, because that breaks gauge invariance, but at the same time they wanted to get rid of the mixing terms also directly by using a proper gauge fixing term. And that is possible. And let me immediately tell you the solution, which is the so-called R-psi gauge fixing term. It looks like this in the generic case: 1 over 2 psi times d mu VA mu, so like in QED, but then we have an additional term proportional to the Goldstone fields, namely minus zeta times GA, and the whole thing is squared. So you have here a linear combination of the d mu a mu for each gauge field times the minus the corresponding Goldstone field. And here there are two coefficients, psi and zeta. And let us work out what that gauge fixing term will give us in the end. It will give minus 1 over 2 psi times d mu VA mu squared, the same as in QED. Then a mixed term plus zeta divided by psi times d mu VA mu times GA minus zeta squared divided by 2 psi times GA squared. And now here you see that this gauge fixing term produces also a mixing between the vector boson and the scalar boson, namely VA and GA with a derivative. And that has exactly the same structure as the mixed term coming out of the covariant derivative. Both appear with plus, but once the derivative is here and once the derivative is on the other field, and therefore if you add the two, you get something which is a total derivative, in other words, 0 in the action. In order to cancel this, zeta and psi must be equal. So if zeta is equal to psi, the mixed terms drop out. And that is the R-psi gauge fixing, where you have this term with psi and zeta is in the end set equal to psi. So then we can discuss really the full bilinear Lagrangian in the gauge theory with R-psi gauge fixing instead of unitary gauge fixing. Maybe let me do it with a little bit more space.
طيب هنا نحن عرفنا أن الجيج فيكسين الذي اشتغلناه في المحاضرات السابقة في السلسلة طبعا الناتج كان من ماذا؟ الناتج من هناك unphysical states يجب التخلص منها لأنها لا تظهر في العلن أو هي أدت إلى unphysical states، وهذا ناتج من الكلاس 1 كانت كلاس 1 كلاس 1 جيج انفاريانس أو كونسترين كلاس 1 كونسترين، وكلاس 1 كونسترين ناتج إلى ماذا؟ ناتج إلى أن canonical conjugate لديه أكثر من قيمة في المومنتوم أو في السرعة، يعني المومنتوم لديها أكثر من قيمة في السرعة. وقد عزينا ذلك في نظريتي أن المومنتوم أكثر من السرعة بالنسبة لأنه هناك معدلات تدفق الزمان هي غير واحدة تختلف، وبالتالي السرعة يمكن أن تأخذ قيمتين في يعني إذا انتقلنا من مكان إلى مكان صغير يعني قريب منه، والسرعة ممكن تأخذ قيمتين. بالتالي هذه القيم للسرعة تكون مكافأة لقيمة واحدة للمومنتوم. بالنسبة لفضاء ونحن فضاء الذي نراه، ولهذا وجدنا أنه هذه القيم تعتبر يمكن أن اعتبارها قيم حقيقية، لأنه نحن نتعامل مع فضاء حقيقي، وأن الجيج فيكسين بعملية الفيكس اللي بالنسبة للجيج أخفى تفاصيل منها كما ذكرنا ال والS physical state L وS، ووجدنا أن الS والL أو ال يمكن أن يكون combinations لmany physical أو physical states. وهذا عزيناه إلى أنه إذا اعتبرنا أن ال هذا ال polarization L أو physical state L إذا اعتبرناه حقيقيا، هذا يخبرنا يمكن أن يكون هناك كذا تفاعل أو كذا aggregation أو مثلا تكثف للطاقة في ستيت واحد، وهذا يجعل الفضاء الصناعي الأبعاد يدافع عن نفسه بطريقة أقوى وتخرج لنا جسيمات أقوى وأعنف وأكثر اختلافا من ناحية الكتل في هذا الموضوع. كما رأينا أن هنا المحاضر جعل أهمل النيوترينو، لكن إذا طبقنا الفرضية التي ذكرتها قبل الآن، فهذا يعني النيوترينو يكون له قيمة حقيقية وله لديه كتلة حقيقية، ويمكن حسابها حتى لو كانت هذه الكتلة صغيرة جدا يمكن حسابها بطريقتي التي شرحتها. إذا الجيج فيكسين أخفى معلومات أيضا يمكن الاستفادة منها ويمكن تحويلها إلى يعني يمكن أن نستخدمها في حساب الفرق في الكتل بين الجسيمات التي تخرج من التفاعل عند الطاقات العليا. طبعا هذه كلها عند الطاقات العليا. عند طاقات الدنيا المعادلة صحيحة وكل شيء ماشي تمام، لكن الطاقات العليا تظهر لنا جسيمات أخرى. هذه الجسيمات الأخرى تظهر عن طريق هذه الآلية. كما رأينا هذا الترم بين الجيج جوستون بوزون وبين الفيكتور الفاكيوم اكسبكتيشن فيكتور، هذا فيكتور للفاكيوم هذا تكون في السايد أو في المكان المختص بالمجال الكهربائي المتدفق المعتمد على الزمن. وإذا أخفيته يعني أخفينا جزء من هذا المجال هذا الجانب. وفي النهاية المكانية كم لا تتأثر بذلك، لأن هي تعتمد كليا بالجزء المعتمد على الجزء المغناطيسي المعتمد على المكان، لهذا هو لا تتأثر، إنما تحسب قيمة الكتلة مباشرة من التجربة. لكن إذا جعلناه موجودا مع هذه هي مع جي اي تربيع اللي هو اكساي او زيتا، هذه زيتا على 2 اكساي في جي اي تربيع، هذه الاثنان اذا جعلناهم موجودين فهي تخبرنا بالتغيرات في المجال الكهربائي بالنسبة للمجال المغناطيسي، وهي يؤدي إلى معرفة حسابات التدفقات الكتلية والتغيرات في الكتل بطريقة أفضل.
Here. So then we look at the bilinear Lagrangian for the scalar and vector field sector of the theory. in our psi gauge. Bilinear means that we are looking at the free theory, which gives us the interpretation in terms of Fock spaces of free particles, which then have interactions in terms of Feynman diagrams. And so what we need is, first of all, the covariant derivative term, and on the other hand, this our psi gauge fixing term. And from all of this, we only need the bilinear part. And what do we get if we do it? We, from the covariant derivative, we have this here, which we already discussed. And from the our psi gauge fixing, we get the other two terms. So we get 3 terms plus 3 terms, but 2 cancel. So we get 4 terms in the end. On the one hand, the ordinary kinetic term of all the scalar fields. Capital phi or small phi doesn't matter because the vacuum expectation value has no ordinary derivative. Then we have, let's put maybe the mass term over there, minus 3a, sorry, minus 1/2 3a squared, the last term on the right for zeta equal psi, which would be a Goldstone boson mass term connected with a kinetic term for Goldstone bosons. You have ordinary kinetic and mass terms for the scalar fields, and the Goldstone bosons become massive. Then the mixed terms drop out, and we have a kinetic term minus 1/2 psi for the gauge fields, dVA square, and the mass term plus 1/2 L square AB VA VB. And this is now very easy to interpret and very nice. So as I said, here we have kinetic plus mass terms for the would-be Goldstone bosons. And the mass terms are, sorry, did I miss anything? I think I did. Yeah, sorry about this. There is a remaining psi in the numerator, right? I forgot about that. If we set psi equal to zeta, then there still remains a factor psi here in the numerator. So we get psi-dependent masses for the Goldstone bosons. And here we get an ordinary gauge fixing term, like in QED. And here we then get the mass terms for vector fields. And there are no mixed terms. Therefore, if you now pass to the quantization of this free theory, what happens is you have a free Lagrangian. Free means bilinear Lagrangian with linear equations of motion without any interactions. And this Lagrangian contains parts for scalar fields and parts for spin 1 fields. And all of those different parts of the Lagrangian have exactly the form of ordinary quantum field theory 1 lectures for scalar fields and for massless or massive vector fields. And therefore the quantization of this Lagrangian can proceed exactly in the way as we discussed in the last semester in quantum field theory 1 lectures. And the outcome is of course the identical one, and the procedure as well. So free means bilinear Lagrangian with linear equations of motion without any interactions. And this Lagrangian contains parts for scalar fields and parts for spin 1 fields. And all of those different parts of the Lagrangian have exactly the form of ordinary quantum field theory 1 lectures for scalar fields and for massless or massive vector fields. And therefore the quantization of this Lagrangian can proceed exactly in the way as we discussed in the last semester in quantum field theory 1 lectures. And the outcome is of course the identical one, and the procedure as well. So let me just write this down. Like in QED with this Gupta-Euler formalism. We can quantize as in quantum field theory 1b lecture. For the part involving the gauge bosons, we get negative or indefinite norm states. In the same way as in QED, when we quantize with such a Lorentz covariant gauge fixing, these indefinite norm states, partially negative norm states which have no physical interpretation, they are of course unphysical degrees of freedom. And like in QED at the time, we therefore must define a subspace of the Fock space which corresponds to a Hilbert space with positive norm on which we can interpret physics. Must define a positive norm physical Hilbert space as a subspace. And how we are going to do it is a question for later. But at this point, we first of all see that these RXI gauge fixing terms are possible. They are easy to formulate in the generic case, therefore also in each concrete case, like in the standard model, we could easily write them down. And if we use them, then we get a Lagrangian which can be very well interpreted. In particular, now there is no mixing between spin 1 and spin 0 anymore, and therefore the mass term for spin 1 can of course be interpreted really as the physical masses of the spin 1 particles. Yeah. Mm-hmm.
Now we did choose a gauge.
Right. You're right, and they correspond to these indefinite norm states, which then ultimately cannot be part of the physical Hilbert space. But we cannot at this point see in an obvious way, unless you are very experienced maybe, how they end up in this unphysical sector of the space. But that they are simply set to 0. Right. And let me compare this maybe to the case in QED. In the case of QED, you could, for example, choose axial gauge, where you set A3 equal to 0. If you set A3 equal to 0 in QED, that is possible. If you do it, there are no unphysical degrees of freedom anymore, you know. Then you can write down the Lagrangian with A3 being set to 0. And if you do that, then you are able to quantize that Lagrangian, and if you quantize it, there are only physical degrees of freedom in it. The resulting quantum theory immediately contains only positive norm states, which correspond to transverse photon degrees of freedom. And however, you can also do a Lorentz covariant gauge, which is this minus 1 over 2 psi d mu a mu square additional term in the Lagrangian. So you do not gauge anything to 0, but you add this non-gauge invariant term to the Lagrangian, then you can also quantize. The advantage in QED is that the Lagrangian is then Lorentz covariant. But the drawback is that you end up with unphysical degrees of freedom, because now you have 4 gauge boson degrees of freedom in your Lagrangian, but the physical photon contains only 2 degrees of freedom, namely 2 transverse polarizations. So there are 2 unphysical degrees of freedom in your theory description. And if you do the quantization, then you end up with states with negative norm and states with positive norm, which are nevertheless unphysical. And you need to define that subspace structure, as we did in the Gupta-Bleuler formalism. And here it's exactly the same. You can either use unitary gauge, where you gauge away the unphysical degrees of freedom. That is all very nice, and it's even better than in axial gauge, because unitary gauge actually is Lorentz covariant, so that is not a problem. So, but then you have only positive norm states in your theory, or you use RXI gauge, which is similar to that gauge in QED, so then the unphysical degrees of freedom remain in the theory description. That has certain advantages, and you will get negative norm states in your quantum theory, and you need to define the subspace structure. So it's completely analogous.
But how much of a problem is it to make the theory non-Lorentz covariant? You then have to put in some work to see that the physical part is Lorentz covariant.
Now, we indicated that in the last semester. We didn't maybe call it axial gauge, but we looked at a case where we did this we removed out of the photon quantum field operator the unphysical degrees of freedom. Then the quantum field of the photon contained only creation operators for transverse photons. And then that photon field operator was not Lorentz covariant anymore, but it fulfilled a certain other relation, which is similar to axial gauge. And so then we argued what we need to do in order to get Lorentz invariant interactions, which corresponded to gauge invariant interactions. And here you do not see at this point what is the disadvantage of unitary gauge and why we would like to prefer RXI gauges, but I will tell you at some other point. Anyway, for the interpretation and for our purposes that we have used last week, the unitary gauge is perfectly fine, and therefore our results that we have stated for it are of course correct. Good, let us go on. Let us go on. You know what is now going to happen. Namely, we need to discuss this issue of positive versus negative norm states in your theory, and we need to discuss how to extract the physical subspace of states, and the formalism for that is BRST formalism. So now we need to look at the generic BRST structure. And that ties in nicely with the discussion of the other lecture, where we discussed BRST for general Young-Mills theories without spontaneous symmetry breaking, and there I already alluded to that the situation changes a little bit in this context, and now you see how it changes. So let me just contrast this once again. Unitary gauge. Here we have only physical degrees of freedom. And therefore only positive norm states. So we can directly interpret everything in terms of physics. Direct interpretation is possible. But let me now tell you the drawback. The drawback is that in renormalization you have some difficulties. Because the propagators, Feynman rules for propagators of vector bosons, they behave like p mu divided by p square. So they do not go to zero for infinitely high energies, and that messes up the so-called power counting in loop diagrams. In other words, the divergences are much worse than in other cases. Okay, in contrast, arc psi gauge. So see above, we have here indefinite norm states, just like we had in quantum field theory 1 in the case of QED. This happens now all over the place. And we need to construct a physical subspace. And we do that by using BRST invariance. So we need BRST invariance to obtain a structure in our theory which allows a consistent definition of this physical subspace. When I say consistent, I mean consistent with interactions. We need to define a physical subspace. It should be consistent with interactions. In other words, interactions do not bring us out of that physical subspace. And that is in particular manifested in the unitarity of the physical S matrix. So the S matrix must be restricted onto the physical subspace. Then it is some operator on the physical subspace. It shouldn't lead out of the physical subspace, and it should be unitary on the physical subspace. These are very non-trivial demands, and in order to fulfill those demands, we have to use the BRST formalism. Therefore, let us go through that structure.
طبعا البي ار اس تي خصوصا في اليانغ ميل ايكويشن فيها مشاكل كما رأينا في فيديوهات سابقة أنها يعني تعطينا نيجاتيف نورمز، وزي ما ذكرت أن النيجاتيف نورمز هذه تعتبر حقيقية ولكنها ليست في النورمز إنما في النورماليزيشن كونستانس اللي هو أو في البري فاكتور التي هي عبارة عن جي ميو نيو، فهي تأخذ الشكل النيجاتيف. وأيضا ذكرنا إنه اس ماتريكس يونيتاريتي يجب أن تكسر إذا أردنا أن نتحدث عن التفاعلات دون الذرية في الريال تايم، يجب أن تكسر، لأنه نحن هنا نحتاج أن ننظر كيف تتطور الماس، وبالتالي في حالة تطور الماس يونيتاريتي بتكسر، وعندما تستقر الماس يونيتاريتي بترجع مع زيها مثلها ومثل أي سيمتري آخر. فالبي ار اس تي تضيف لنا معلومات جميلة عن ما يسمى بالجوست بارتيكلز مثل السي والبي. وذكرنا أن السي والبي يمكن أن تكون عبارة عن combination of AMU اللي هو of spin one particles، عبارة عن combinations. هذه combinations تعتبر حقيقية، لكن الفضاء صناعي الأبعاد يحاول يفرغها لأنها تعتبر طاقة مكثفة، وبالتالي تظهر لنا طاقات أسرع من بقدر سرعة الضوء وأسرع من الضوء بسبب هذا التفاعل القوي جدا بين الفضاء صناعي الأبعاد وبين هذه الجوست بارتيكلز. فلهذا كتبت كتاب عن هذا النوع الماسيف بارتكلز تسير بسرعة الضوء ناتج من هذا النوع من التفاعل، وأن النورم النيجاتيف نورم ناتجة من هذا النوع أيضا هذا النوع من التفاعل، لأنه الجي ميو نيو عندما تقلب هذا يعني أننا دخلنا إلى تفاعل قوي جدا جدا، وبالتالي يظهر هذا النوع من التفاعل. وهذا يطابق مع ما ذكرناه عن الكتل، أو انتقال من المجال الكهربائي للمجال المغناطيسي داخل الكتل، حيث أن داخل الكتل أو داخل التفاعلات تتحول المجالات الكهربائية لمغناطيسية أو تضمحل المجالات الكهربائية على حساب أو في صالح المجالات المغناطيسية، وبالتالي يمكن إعزاء هذه التغيرات الكبيرة التي تأخذها ايجاد ميل إلى هذه المجالات المغناطيسية وتفاعلاتها.
So let us directly write down the BRST transformations. We need to introduce ghosts, so-called Faddeev-Popov ghosts, called CA of X, ghost fields for each generator A. Then we define the BRS transformations in terms of this operator small s. Small s generates infinitesimal BRS transformations, and we define it such that if S acts onto any field, phi, then we get CA times the gauge transformation in the direction A of that corresponding object for phi is any of the fields, VA, mu, or scalar field, or other matter fields. Okay, so for all the ordinary fields of the theory, the BRST transformation is just a gauge transformation where the transformation parameter is replaced by the Faddeev-Popov ghost field. Then the BRST transformation of the ghosts themselves are defined such that S square acting onto phi is always 0 for all fields phi. So that uniquely fixes the BRST transformation of the Faddeev-Popov ghosts. They are proportional to the ghost square times structure constants, but let us not write this down. You can find this in the other lecture. Then we have also anti-ghosts and auxiliary fields. C bar A of X and BA of X. The BA of X is an auxiliary field which can always be eliminated by its equations of motion, but it's useful to introduce it as an abbreviation, and whenever it appears in the Lagrangian, you can at the end replace it by its value coming from the equations of motion. And they are defined such that S acting on CA is B and S acting on B is 0, such that again S square acting on anything is 0. Okay, then using this formalism, we have now a way to introduce a BRST invariant RXI gauge fixing. Namely, we introduce gauge fixing not in isolation, but the gauge fixing must be accompanied by certain interaction terms for the ghosts, such that the total combination of them is BRST invariant. And that can be achieved by writing the whole combination of gauge fixing plus ghost terms as a total BRST transformation of something, because S square is 0. Therefore, if we have S of anything, the BRST transformation of that will be S squared of something and therefore 0. So this is the generic way to introduce a BRST invariant gauge fixing term. And we should now put into the square bracket something such that its BRST transformation generates the arc psi gauge fixing term. And then inevitably there will be some extra terms which will be necessary ghost interactions that make the whole theory BRST invariant and which then allow these things here. And what can we put there? It's standard psi over 2 times BA with this auxiliary field plus BA times FA, where FA is the desired gauge fixing term. Which was here B mu VA mu minus zeta times these generic Goldstone fields GA. So if we define it in this way, then we get here, I'm sorry, misprint, sorry. CA bar. So if we now evaluate the square bracket, then what we obtain from the first term, BRS transformation of C bar gives B, BRST transformation of B gives 0, so the only thing that we obtain from the first term is psi over 2 times BA. And from the second term, we obtain the BRST transformation of the ghost gives BA times FA. And then we get minus because S and C bar are fermionic, so we get minus C bar A times the BRST transformation of the gauge fixing term FA. And now you'll see what I told you before, the B is an auxiliary field, so it appears in the Lagrangian in this trivial way. So the Euler-Lagrange equation of motion for BA is simply the following. So there is no derivative term involving B, it's just a non-derivative term. So the Euler-Lagrange means derivative of L with respect to B must be 0, then we have psi times D plus F is 0, in other words B is minus 1 over psi times Fa. And if we plug it in, then we get the famous minus 1 over 2 psi times Fa square minus C bar A times BRS transformation of Fa. And then you see that here, in principle, you could choose any desired gauge fixing term, but you can choose the arc psi gauge fixing term. Then you reproduce here the desired arc psi gauge fixing that we want. And here, as I said, you inevitably obtain something else which contains ghosts. And whatever is the BRST transformation of this Fa must be put here. It might be 0 in some cases, but here it's not 0. And anyway, it's something proportional to ghosts, because here is an empty ghost, and all the BRST transformations are proportional to some ghosts. Therefore, that corresponds to a ghost-anti-ghost interaction with something to be evaluated. So let's simply comment on that. This is the desired arc psi gauge fixing term. Ghost interactions needed for unitary S matrix. Okay, and using this, we have now the full gauge fixing plus ghost Lagrangian of our theory. We can come back to the physical interpretation. And here I will just do a sketch and refer also to the exercise. And the exercise in turn also refers to the other lecture, Quantum Field Theory 1 and Quantum Field Theory 2, where we have discussed exactly the same structure, first for QED in the last semester, and then for generic Young-Mills theories in this semester. And here we just look at a sketch of the changes for the spontaneously broken case. So first of all, we can quantize this. Like in the Gupta-Bloiler method. We will obtain negative norm states. We already said that. But the same is not only true for the unphysical Goldstone and vector boson degrees of freedom, but also for the Faddeev-Popov ghosts. They also contain indefinite norm, partially negative norm. And the physical fields in the free theory, to say it simply, they are defined by the linearized BRS transformations as linearized where you neglect all terms which are quadratic or higher powers in the dynamical fields. Only for the free theory, only the linearized parts in the BRST transformations matter. And then the physical states could be basically written as a quotient space kernel of these linearized BRS transformations divided by the image of the linearized BRST transformations. And then you get the following structure, and I think I can sketch that here. Massless photon on the one hand, and massive vector bosons and Goldstone bosons would be Goldstone bosons on the other hand. So what is the structure of the linearized BRST transformations? In the massless case that we discussed last semester, you could decompose a photon field into a scalar part, S mu, plus a longitudinal part, L mu, plus 2 transverse degrees of freedom, T mu 1 and 2, corresponding to the polarization vectors epsilon mu in the decomposition of the corresponding field operator. Okay, and if you discuss that, then, for example, for a massless photon, what happens if you do d mu a mu in the massless case? D mu a mu, the scalar thing would be proportional to a derivative. Then that gives 0, and so this d mu a mu only reproduces the longitudinal part of the photon field, and all the other parts, the scalar part and the transverse part, they are transverse. And then by looking at the details, you will see that the linearized BRS transformation behaves as follows. So the transverse degrees of freedom, they are mapped to 0, so they are BRST invariant. Then on the other hand, the anti-ghost under BRST becomes B, but B is eliminated by the equations of motion to d mu a mu, and d mu a mu here is the longitudinal degree of freedom, and on the other hand the scalar degrees of freedom goes into the ghost. And then you have here the BRST quartet. Let me write it here. BRST quartet, which is unphysical because this is not BRST invariant because it transforms into this. This is in the image of BRST and therefore also unphysical. This is not BRST invariant, and this is in the image, and therefore all of them are unphysical. And here you have physical states. Physical states which are BRST invariant and which are not in the image of the BRST operator. So this is the structure in QED as we have discussed it. Now what happens here? Here we can again decompose a mu as a scalar part plus a longitudinal part plus two transverse parts. But because it is massive, the structure of these scalars and longitudinal, they are different. So here, according to our polarization vectors that we have defined elsewhere, we would say the longitudinal actually is the longitudinal is defined also in a transverse way. So the polarization vector is longitudinal only in the three-dimensional sense, but the fourth component is defined such that it still is transverse, whereas this can be written as the derivative of something else. And then if you look at the BRST transformations, then you see that under the linearized BRST transformations, again the transverse degrees of freedom, they are mapped to 0. However, now the longitudinal degree of freedom is also mapped to 0, which means that we have now three physical vector degrees of freedom, transverse and longitudinal, where longitudinal is defined in that sense, different from this sense here. And then we also have a BRST quartet, namely what happens if we start from an anti-ghost. The anti-ghost becomes B, but B will be eliminated to a linear combination of d mu, v mu and the Goldstone field. So C bar becomes the scalar plus Goldstone, and on the other hand the scalar itself goes into the ghost. And then you see that the Goldstone is unphysical because it is in the image. The scalar degree of freedom is unphysical because it's not BRS invariant, and the ghost and anti-ghost, they are also unphysical. So you see here how the degrees of freedom change their structure. The longitudinal becomes physical and was before unphysical, and the Goldstone degrees of freedom, they go into the image of the BRST transformations given in the linearized form, and therefore they become unphysical. And looking at this in detail is your job for the exercise. But anyway, I think this is quite beautiful that this maybe a little bit abstract formalism can really also tell you the longitudinal becomes physical and was before unphysical, and the Goldstone degrees of freedom.
هذه معلومة طبعا تؤكد ما ذهبت إليه، أن اللونجيتودينال تعتبر تصبح فيزيكال في هذا النوع من التفاعلات. لماذا؟ لأنه نحن قلبنا الأبعاد، هذا ما ذكرته سابقا، الأبعاد انقلبت بسبب الكتلة والخواص الكهربائية أصبحت قوات مغناطيسية، والجي ميو ذهبت من الموجب إلى السالب. بالتالي هذه الأبعاد الطاقات العالية، هذه المتغيرات خصوصا اللونجيتودينال لا يمكن إلا أن تكون فيزيكال في هذا الموضوع. وهذا ما ذكرته في كتابي حلقة 54 عندما تحدث عن الياج ميل equation.
They go into the image of the BRST transformations given in the linearized form, and therefore they become unphysical. And looking at this in detail is your job for the exercise. But anyway, I think this is quite beautiful that this maybe a little bit abstract formalism can really also tell you about the physical structure of the degrees of freedom. Okay, if we have, we have only 3 minutes of time, but maybe I can just tell you a little bit how it looks like in the actual standard model. Okay, so very quickly. So in the electroweak standard model, we have in general the following covariant derivative of our Higgs doublet in the standard model. So we are now back in the standard model, and capital Phi denotes the well-known two-component Higgs doublet. And we now evaluate this covariant derivative in general, not in unitary gauge. We discussed the last time how it works in unitary gauge, and here the differences are minimal, and I will immediately give you the result. You get the ordinary derivative plus I, and then in the upper component you have MW times the W plus mu field, and in the lower component minus mz divided by square root of 2 times the z mu field. And you can collect the terms in a different way, namely the ordinary component of, okay, this is only the linear part, of course, so products of fields are neglected. But then let's split the derivatives into the derivatives of the unphysical Goldstone field and the physical Higgs field. Then for the physical Higgs field, we simply have in the lower component derivative h divided by square root of 2. And then we have the following vector, which now contains the vector boson terms and the derivatives of the Goldstone fields. So for example, in the upper component, we have the derivative of G plus I times MW times W plus mu. Okay, so this linear combination. And in the lower component, we have I divided by square root of 2. And then we have on the one hand the derivative of the neutral Goldstone field G0, and on the other hand minus mz times z mu. Okay. And that's it. And then you see now that actually there are certain linear combinations emerging, namely a linear combination between Goldstone derivatives and vector fields. And it is only those linear combinations which appear. W does not appear in isolation. Derivative of Goldstone doesn't appear in isolation. They only appear in terms of this linear combination. So this typical form, derivative of Goldstone plus vector field. And then if we square this in the Lagrangian that appears squared, then of course what happens is we get the square of the upper component plus the square of the imaginary part plus the square of the real part. Therefore we get exactly the squares of those particular linear combinations, and that will create the famous mixed terms that should be cancelled by our psi gauge. So let me also say this. This will give rise to mixed terms in the square of d mu. And so then I will just write down the arc psi gauge fixing for the standard model, and then I think we can stop. So we would have 1 over 2 psi a for the photon times Fa square for the photon minus 1 over 2 psi z times Fz square for the z minus 1 over 1 psi w times F plus F minus for the W boson, and then this is d mu a mu for the photon. This is the same for the z, d mu z plus the corresponding linear combination, which cancels exactly that mixing term, which is minus zeta z times mz times Goldstone field G0. And here the F plus would be d mu W plus mu for the W boson, plus the corresponding Goldstone term to cancel the mixed term here, minus I times MW times G0 times zeta w. And then for zeta I equal psi I, the mixed terms drop out. And then you have it. This is the arc psi gauge fixing for the electroweak standard model with exactly those particular terms. And if we use them and set psi equal to zeta, then we have the nicest Lagrangian for the quantization of the electroweak standard model. And like in the generic case, this will automatically generate particular Faddeev-Popov-Ghost interactions via BRST invariants. They are unique by applying that formalism and can be evaluated, and then we obtain certain interactions between Faddeev-Popov-Ghosts. But let us not go there. I will add this small information the next time. Okay, but let us stop here. Thanks and see you in the afternoon.
طبعا المحاضرة كانت مليئة بالمعلومات ومفاجآت، لكن هناك أشياء طبعا فاتت علي كثير نسبة للإزعاج الذي كان بجنبي. لكن أنا يعني أهيب بالعلماء أن يبحثوا في هذه المحاضرة بحيث أنه يعني يستطيع يستخلصوا أشياء ترتبط بنظريتي فاتت علي لم أذكرها، وستكون من الأهمية بما كان. يعني مثلا ماذا يحصل إذا كانت الزي لا تساوي السي أو الإكساي؟ ماذا يحدث؟ أكيد لها علاقة بالمجالات المغناطيسية، أكيد لها علاقة بالفري ديجريز اوف فريدم في المجالات المغناطيسية، لكن أنا لم أستطع أن 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 ألمح هذا الموضوع. وهناك أيضا حدود تتعلق بهذه التفاعلات المغناطيسية مع بعضها البعض أيضا لم ألمحها. فأنا أرجو من العلماء أن يحاولوا أن يبحثوا في هذا الموضوع وأن يلمحوا هذه الأمور. السلام عليكم ورحمة الله.